In section 5.3, we're looking at angle bisectors of triangles and angle bisectors in general today. First of all, what does it mean to be an angle bisector? Remember, bisector means cut something in half, so an angle bisector divides an angle into two angles that are congruent. An angle bisector divides an angle into two congruent angles. So I'm going to start out and just put a sketch here. If I would create an angle, and let's say I want to put an angle bisector in there. So I want to divide it into two congruent angles. And you should be thinking, to make it look like an angle bisector, it should be going through the middle. This is obviously closer to the vertex, or excuse me, closer to the ray above. If I went down here, it's closer to this ray below. So I just want to be as close to the middle as I can to make it look like an angle bisector. I prove it's an angle bisector by showing that I do have two congruent angles and putting the same number of arcs in those angles. So now we have an angle bisector. Something else I need to remember and be familiar with today is if you're talking about the distance from a point to a line, you have to measure at a certain angle. Let's say we want the distance from this point to this ray. How would you measure it? Well, you don't just grab any old distance and say, there's the measurement, I'm going to measure this, we're good to go. Well, no, and you wouldn't just measure here. Remember that the angle you should be measuring at, or the closest distance, shortest distance from a point to a line, is measured at a right angle, also along a, what is that called when you meet at a right angle? Perpendicular. And this will be important today, that if you are measuring the distance from a point to a line, make sure you're measuring along a perpendicular and that you have a right angle mark there. So, talking about angle bisectors today, what makes them special? Here we have angle bisector theorem. If a point is on the bisector of an angle, then it is equidistant from the two sides of the angle. Angle bisector theorem. So we have a point here. It is on the bisector of the angle because I know this is an angle bisector because of the fact that I have two congruent angles. Therefore, this does bisect or cut this angle in half. I have a point on that bisector. Yes, I do. What I know is since this ray is an angle bisector, that point on that angle bisector is equidistant from the two sides of the angle. Remember, equidistant means the same distance from the two sides of the angle. And if you're going to measure distance to the sides, make sure you're going at a right angle. So I know that this distance here at a right angle would have to be equal to this distance at a right angle. And I could put one tick mark on both of those. If this truly is an angle bisector, then the distance to the sides should be the same. And I could grab another point and put a point, I don't know, how about right here? It is on the angle bisector. So if I do the distance to the sides of the angle at a right angle, remember, because that gives you distance from point to a line, then these two would be congruent to each other. Okay? Any point on angle bisector equidistant to the sides. And you might say, why? Because if you're on the angle bisector, you're literally in the middle of the angle. I think you would agree this would not be the angle bisector of the big angle. And every point on here is going to be closer to this ray. And if I was over here, I bet you could agree this does not look like an angle bisector. Also, any point on this ray would be closer to this side of the angle rather than the one above and to the left. So being on the angle bisector means you're equidistant to the sides because of the fact that angle bisector is literally going through the middle of that angle. On the next slide, we just have the converse of this theorem, which we know switches around the if and the then. So here we have, if you have a point somewhere in the interior of an angle, right, it's somewhere inside this angle, but if that point in the interior is equidistant from the sides, which this point is equidistant from the sides of the angle, because I see that we have tick marks on these segments that are going at a right angle or a perpendicular to both sides. So let's see, I fulfilled the hypothesis, right? I have a point in the interior of an angle that is equidistant from the sides of the angle. Then, what do you know? Then this point lies on the angle bisector of the angle. If this is true, and this point really is equidistant to the sides, again, I know that because I see congruent tick marks at a right angle to the sides, then if I drew in a ray through that point, I know that's an angle bisector. No, this is an angle bisector. Because if that point is equidistant to the sides, it must be on the angle bisector, and I could say that these two angles are congruent. So angle bisector theorem and the converse, let's put those to use. Find the measure of angle BAC. Okay, where's angle BAC? B to vertex A out to C. Actually, angle BAC is this entire angle here. Now I know this angle here is 54 degrees. Angle DAC? How can I find angle BAC? Now nothing in here, this does not say it's an angle bisector, so I don't know that this is 54, or do I? Well, I have this point D marked out here, and I have 18 is the distance from D to both rays, both sides of the angle. It is measured at a right angle, both 18. Hey, then this must be the angle bisector of this angle. And I know this is an angle bisector by the converse of the angle bisector theorem, which says that if you have a point that is equidistant to the two sides of an angle, it has to be on the angle bisector. Therefore, I know that these two angles in here are congruent. So now I can find angle BAC because I know that this guy is 54 degrees as well. Angle BAC is the whole thing, 54 times 2, or 108 degrees. Okay? So converse angle bisector theorem, I knew that this was an angle bisector, it was equidistant to the sides, and I could use that to find our angle measure. An example here, we have 3 spotlights. We're like on a stage in this case. And the spotlights are going to the stage in these 3 locations. The spotlights form 2 congruent angles. So they're telling me these 2 angles are congruent. Is the actor closer to the spotlighted area on the left or the right? So basically, which of these distances is closer? Well, if we do have an angle bisector, which this is, right? So the actor is on the angle bisector. There is actually a problem with this example. And the book's going to say he's the same distance from both, he's on the angle bisector, but remember that technically we need to know that the distances are both going at a perpendicular to that side, or at least that they're going at the same angle, because I need to know that these triangles are congruent. If you really think about it, back here, we know that these angles have to be congruent by, well, I guess it's side-side angle, but it'd be hypotenuse leg. Okay, we have a right angle, we have the hypotenuse being congruent because it's shared in both triangles, and we have one of the legs congruent. Well, going here, to know that these triangles are the same, we have to know that these angles are congruent. So we have angle, angle, side, and that would prove they're congruent. So really, I need to know something else. Or I need, well, to know if this is the same distance, I need to know one of these angles. That one pair of corresponding angles are the same. Need to know that one pair of angles is congruent, technically, or that he's at a right angle to both. Because that is an important factor. We know that the angle bisector theorem is telling us we have to be equidistant to the sides measured at a perpendicular, or at least measured at the same angle. So as of right now, you don't really know for certain whether he's closer to left or right. Alright, let's see here. For what value of x does point P lie on the bisector of angle A? So I want P to be on the angle bisector, like I want ray AP to be the angle bisector. Well, what value of x would make that true? You notice that from P, x plus 8 is the distance, because it's at a right angle to the side here, and 3x minus 6 is the distance from P to this side of the angle, because again, it's at a right angle. Well, what do you need? You need the distance from P to the sides to be the same. I need P to be equidistant to the sides, because then by the converse of the angle bisector theorem, P would be on the angle bisector. I'm just throwing in letters. Need P to be equidistant to the sides of the angle. So, what I want to have happen is that x plus 8 would have to be the same as or equal to the distance 3x minus 6. And solve and find x. So I'm going to subtract x from both sides, get rid of it from the left. 3x minus x is 2x. Minus that 6 equals 8. I'm going to add 6 on both sides. 8 plus 6 is 14. Equals 2x. Divide by 2. And x equals 7. And we're good to go. That's converse of the angle bisector theorem again, that we need a point to be equidistant to the sides than it is on the angle bisector. And another example here, let's find x. The arrows are showing that 3x plus 5 represents this angle and 4x minus 6 represents this angle. Well, let's see, do I know anything about these angles? If I take a look here, I notice from this point, these two segments are marked congruent from the tick marks. These two segments do go at a right angle to the sides. Therefore, the distance to the sides is the same from this point. Distance to the sides is congruent. So this is an angle bisector, right? This is the angle bisector theorem. Or a converse angle bisector theorem, sorry. Therefore, these angles are congruent, and I know that 4x minus 6, that angle has to be equal to or congruent to 3x plus 5. Solve for x, subtract 3x, it's gone from here. 4x minus 3x is just x, minus 6 equals 5, add 6 on both sides, and x equals 11. So working with angle bisectors and realizing that they're equidistant to the sides of an angle measured at a right angle.